Okay, let's unpack this. So we are diving into a problem that's truly massive, but often kind of invisible: e-waste.
Yeah, massive is the word. We're talking about every single discarded electrical device you can think of. Old printers, broken phones.
Kitchen appliances, TVs, the works. And if you've ever tried to figure out how to responsibly get rid of, say, an old television, you know it's a real headache.
Absolutely. And the thing is, these objects, they contain incredibly complex components.
Yeah.
Things that are almost impossible to dispose of safely.
Which leads to long-term pollution, right? Stuff leaking into the soil, the water.
Exactly.
Yeah.
And posing severe threats to human health. It's a serious issue.
But what's really striking here, and what our sources dig into, is that this isn't just an environmental thing. It's hitting economics and resources hard, too.
That's a crucial point. We're basically locked into this global cycle of needing more and more tech. We depend on it.
We really do.
But the natural resources needed to build all this stuff, especially those, niche, rare elements that make modern gadgets perform so well, they're finite.
Right. There's only so much to go around.
So this deep dive today, it really confirms that reuse and recycling, well, they aren't just nice-to-haves anymore. It's becoming an urgent necessity for conserving resources, stabilizing costs.
Precisely. And that brings us to our mission today. A deep dive into this really fascinating educational document. It details a specific, high-stakes design challenge.
From an academic competition. Yeah.
Exactly. It's called Turning Electronic Waste into Scientific Opportunity. And this project, it doesn't just ask people to, sort their recycling better.
No, it flips the whole thing.
Okay.
It demands real scientific innovation, built basically from scratch, using waste as the primary building blocks.
It's quite radical, really.
And the core question driving it all is what gives it such weight? How can old, used, or discarded electrical devices be effectively reused to improve the scientific and technological environment for all?
That's the key phrase, improve the scientific environment. It moves way past just theory.
It mandates practical, high-level scientific output, basically using what we've already got lying around.
Yes. So, connecting this to the bigger picture, this isn't some isolated school project, is it?
Not at all. This capstone challenge, it's specifically designed to tackle several critical national goals, referred to as the Egypt Grand Challenges.
The Grand Challenges, okay.
Yeah, it's a holistic approach, meaning the project has to sort of hit multiple targets with one effort.
Like what kind of targets?
Well, we see 4 major ones being addressed at the same time in this design brief. First, obviously, improving the scientific and technological environment. That's core.
Okay.
But teams also have to be actively working on reducing pollution, the stuff fouling up air, water, and soil.
Makes sense. Tied directly to the e-waste source.
Exactly. And crucially, the outcome also has to connect to reducing or adapting to climate change effects. And it needs to demonstrate recycling waste for both economic and environmental benefit.
Wow. That's a lot to pack into one student project. It really shows how science application can drive solutions for these big societal problems.
It really does. It connects, a bit of discarded electronics directly to a national climate goal. Pretty powerful framing.
So the operational objective then, the actual task for the teams, is quite tangible.
Oh, yeah. They're tasked with designing and building a small, reliable scientific prototype. And the key word is reliable. It has to demonstrate the practical potential of reusing components from old devices.
To create a functional system that actually supports research.
Right. And we're not talking about building some generic gadget or toy.
No.
No. The challenge requires students to investigate fundamental scientific instruments, the kind you'd actually find and use in specialized labs.
Okay, like real lab equipment.
Yes. They have to pick a real instrument used in biology, chemistry, earth science, physics, or fabrication labs, and then figure out how to build a working version using salvaged parts.
That's where the practical scavenging and engineering really come in, I guess.
Definitely. It forces them to move past abstract ideas and get their hands dirty dismantling things, identifying useful materials.
So tell us about the scavenger hunt part. What are they allowed to pull parts from?
Well, that's what's kind of amazing. The source list is incredibly broad. It's almost anything electrical you'd find around you.
Like what?
Think typical office gear.
Yeah.
Printers, scanners, projectors, copiers. Then consumer electronics, TVs, computer hardware, mobile phones.
Old laptops, monitors.
Yep. And even everyday household stuff. Chargers, heaters, boilers, ovens, microwaves, mixers. If it plugged in or used batteries, it's likely fair game.
The thought of pulling a critical component for a precision physics instrument out of, like, a 10-year-old dusty kitchen mixer, that's pretty cool.
It is,
Mhm.
but they aren't just grabbing the outer shell, you
Mm.
know. They have to perform actual surgery to extract specific functional pieces,
Right, the useful nuggets inside.
and they absolutely must use a wide range of these extracted components in their final prototype, covering the whole spectrum electrical, electronic parts.
Mechanical parts, too, like
Yeah.
gears or motors.
Yes. Mechanical, optical components, think lenses or mirrors, maybe from an old scanner, and thermal parts, like heating elements or cooling fans from an oven, or maybe a fridge.
That specifies even simple stuff, right? Like screws and wires.
Absolutely. Sensors, fans, wires, cables, covers, holders, screws. The list includes everything. It really forces them to see the potential value in every single bit of junk.
Okay, let's talk about the actual rules for the prototype itself, because you mentioned the rigor starts there.
It does. So rule one, the final instrument must be a single scientific prototype designed for a specific use in one of those lab types we mentioned: bio, chem, earth science, physics, fab labs.
So it can't be some weird hybrid thing that doesn't really do anything useful scientifically.
Exactly. Needs a clear, focused purpose. And the component mix is strictly defined too, which is crucial for proving the whole e-waste reuse concept.
How so?
The final prototype must incorporate multiple components sourced from old devices, not just one or two. And critically, at least one of those used components must be an electrical component.
Ah, okay. So that stops them from just building, say, a wooden box with salvaged screws and calling it done. Needs some functional electrical element from waste.
Precisely. It ensures some level of technical complexity using the e-waste.
And there was a specific rule about thermal instruments, something extra they had to do.
Yeah, that one's interesting. If a team decides to build a prototype dealing with heat, maybe a small lab incubator or a heating bath, something like that,
Okay.
it must include an additional function that's compatible with that main thermal function.
Why force that? Why not just let them build a simple heater like a hot plate from old parts? What's the goal there?
That constraint, I think, is quite clever. It pushes the students towards thinking about integrated design and efficiency. That's essential in modern scientific tools, right?
True. Things usually do more than one thing.
So you can't just build a simple heater. You have to integrate maybe temperature monitoring or perhaps a stirring mechanism using a salvage motor or even a timer. Using salvage sensors and parts, it promotes system-level thinking, not just sticking components together.
Got it. Okay, now you said this is where it gets really interesting. The success criteria. It's not just about making something that works.
Not even close. They demand genuine scientific rigor, demonstrable, almost publishable quality output.
Wow. Okay, how do they measure that?
Well, look at the functionality and application rules. They spell out exactly how usefulness must be proven. If the instrument has only one measurable function,
Like, it only measures temperature.
right, then the team has to present measurable results from two separate actual laboratory applications using it.
2 experiments. Okay.
But if the instrument has multiple measurable functions, maybe it measures temperature and light intensity, they still need to demonstrate at least one real laboratory application.
So they can't just say, look, it turns on and measures temperature. They have to show the data it gathered doing real science.
Exactly. It bridges engineering with actual scientific practice. And if they include any sensors like temp sensors, light sensors, whatever they salvage, they must be calibrated.
Calibrated,
Meaning checked and adjusted against standard methods or known accurate instruments to prove their salvage sensor is trustworthy. And this calibration process, it has to be documented and actually demonstrated on evaluation day.
that adds another layer of scientific discipline.
It does. And they also need to perform a deep electrical characterization of their scavenged machine.
What does that involve?
Teams have to demonstrate the primary electrical characteristics, the necessary operating voltage, the maximum operating power it consumes, and something specific called the maximum drag electric current.
Okay, hold on. Maximum drag electric current. What exactly are they measuring there? Is that like how much power load the salvaged wiring or parts can handle before things, melt or fail?
That's exactly it. It's a critical safety and reliability check. It makes sure they understand the limits of the stuff they salvaged. They're finding the maximum current the system can draw, underload the drag, without causing damage or a big voltage drop.
That's pretty advanced analysis, actually. Proves they didn't just randomly hook up wires. They actually engineered a circuit, considering the limits of the salvaged parts.
Non-trivial stuff, yeah. And then there's transparency, literally. The housing or cover for the prototype instrument, it has to be made from transparent material.
Why is that? Just so it looks cool, or is it like a security measure to stop them sneaking in new parts?
Probably both, really.
Yeah.
Instructionally, it makes them think about the internal layout, accessibility,
Hmm.
making things neat inside.
Right.
But yeah, it's definitely an accountability thing too. Makes it easy for judges to see the insides, the actual salvage mechanisms, and confirm they aren't just brand new off-the-shelf components hidden in a black box.
Can they buy the transparent material, or does that have to be salvaged too?
The doc says it can be extracted, manufactured, or purchased. So they have options there, but the transparency itself is mandatory.
Okay. And documentation, I assume, is crucial.
Oh, absolutely. Documentation is king here. They need professional-level schematics, diagrams showing the external and internal structural design, plus the complete electric circuit diagram if there is one.
Standard engineering practice.
And when they present results from their tests and lab applications, they have to use graphical fitting methods with a minimum of 5 data points, 5 readings.
Graphical fitting. So plotting the data, drawing trend lines or curves.
Exactly. Standard scientific practice again. It's not enough just to list numbers. They have to visually represent the relationship between variables, fit a model to it, show they understand data analysis.
But the real kicker, the number that seems to define success here, is the accuracy requirement, isn't it?
That's the one. Their accuracy calculation cannot exceed plus or minus 5% and 9 by 5% when compared to a functional known standard device.
Plus or minus 5%.
And they have to provide the precision calculation as well,
Yep.
which is related but measures the repeatability.
Okay, that high 5% accuracy, that seems incredibly tough to achieve with parts pulled from, a 10-year-old projector or a broken microwave.
It is. That is probably the single most critical and most challenging part of this whole document. Because hitting 5% accuracy with a machine built from junk fundamentally challenges the whole idea that scientific tools have to be brand new, expensive, manufactured items.
Right. It suggests there's massive untapped value just sitting in our e-waste, way beyond just scrap metal prices.
Exactly. This mandate forces rigorous quality control on those salvaged parts. Selection, cleaning, testing, calibration. It has to be meticulous.
I get the idea, the value proposition. But logistically, isn't there a risk that such a high bar discourages teams? I mean, extracting delicate optics or sensors from dusty, maybe corroded old stuff and hitting 5% accuracy sounds almost impossible.
Well, it definitely sets a high bar, yes. But that's kind of the point of a grand challenge, isn't it? It validates the output. If you manage to build a device from waste that meets a commercial standard of accuracy, well, then you haven't just recycled something. You've actually created potential wealth, scientific capability, where it seemed like there was none before.
So it forces them to be incredibly careful, validating the whole concept.
Precisely. It reinforces the whole ethos, resource conservation through high-quality, demanding application.
Okay, this raises an important question then. How do they balance this really high standard for innovation and scientific output with, safety rules and resource limits during the building process?
Yeah, that's crucial. Safety is absolutely paramount, especially given the source materials. The document is very explicit about adhering to all safety rules.
Especially around high voltage.
Definitely.
No.
High voltage equipment is present in some old devices, so during that component extraction phase, you're dealing with potentially hazardous stuff. Need serious awareness, proper procedures, supervision.
And they have to do everything on site, right, in the school lab.
Yes, completely contained. All processes, from pulling the first component out of an old printer to testing the final prototype in a simulated experiment, it must happen inside the school laboratory.
And they can't borrow or take equipment from the lab itself?
Nope. No equipment belonging to the existing labs can be removed. That location rule serves multiple purposes, really.
Like?
Supervision, obviously. Safety, but also standardization. It ensures any testing they do happens under controlled, standard conditions, which backs up the validity of their calibration and accuracy measurements, you see.
Right, keeps everything consistent. Are there specific things they're not allowed to use?
Yes, very clearly stated. It is explicitly not allowed to use materials containing radioactive elements or hazardous chemicals.
Which could potentially be in some older electronics, depending on when they were made.
Could be. So they really need to know their source materials, or at least test and verify. It demands careful selection.
Okay. And finally, what about exhibition day, getting the thing there and showing it off?
Logistics are tough there too. The final prototypes have to be testable, workable, reliable, and portable. They need to actually function on the day.
And be movable.
Right. And teams are responsible for bringing their own spare parts for anything easily damaged. So if a salvaged fan motor gives out during the
I
demo,
need a backup ready to swap in.
exactly, to prove the concept still works. Plus, hard copies of every team member's logbook are mandatory for verifying the whole design, build, and testing journey.
Wow. Okay, so stepping back, what does this all mean? This deep dive, it really shows a phenomenal kind of multi-layered model, doesn't it?
It really is.
Taking this huge global pollution problem, e-waste, and turning it into this tangible learning opportunity, one that hits national resource goals, climate goals,
While forcing students to apply real physics, engineering, chemistry.
to literal junk, discarded household objects, but holding them to incredibly high scientific standards like that 5% accuracy, it's quite something.
It really moves so far beyond just simple upcycling. This is mandated scientific utility, mandated rigor. It fundamentally challenges how we define waste.
By demanding that these discarded things yield new, measurable, reliable capabilities.
Exactly. And think about the long-term impact, the provocation here. If a reliable scientific instrument capable of hitting that strict 5% accuracy benchmark can be built entirely from components we just throw away every day,
Yeah.
then what is the true, uncalculated value of all that waste we produce globally each year? It suggests it's far more valuable than we think.
So what other essential technologies might be hiding in our junk drawers, in our local landfills?
Precisely. What else is waiting there, needing only a systematic design brief, a challenge like this, to unlock its potential? That feels like the real technological treasure hunt.